Hello, everyone, and welcome to the Ben's Chem Videos Monday night live stream. Normally, I do these things on Sundays, but in an effort to extend my weekend out of town, I decided to do this one on a Monday today. So thank you very much for joining me tonight. We are going to continue our discussion on aqueous ionic equilibrium, and it's been a while since we've talked about this. 2 weeks ago, I did a back-to-school stream, which was pretty unsuccessful. I think I had a peak concurrent viewership of only 4 people, so that was pretty disappointing. And then last week, I decided to take the weekend off. I decided not to stream because I was celebrating the 3rd birthday of my daughter's 3rd birthday. It was a blast. We had a great time. But now I am back and I am ready to continue this discussion on aqueous ionic equilibrium. Very, very excited. So with that, I present to you Aqueous Ionic Equilibrium, Volume 3. As always, your feedback is more than welcome and highly appreciated, so please feel free to leave your thoughts in the chat, or even better, you can call into the show via Discord. There's a link in the description. And if you're watching this as a video, I would encourage you to leave a comment, leave me some feedback. Without your feedback, I am completely and totally lost. All right, so we're going to start by reviewing the content from Volume 2. Let me resize myself a little bit here. So the first couple of volumes, we were talking about buffers, and we're going to continue to talk about buffers tonight. And a buffer, of course, that is an aqueous solution with significant amounts of a weak acid and its conjugate base. And last week, we talked about pH changes in buffer solutions. So if you add a small amount of acid or a small amount of base to a buffer, we know that the pH change will be very, very small, but nonetheless, it does change by some amount. And so we learned how to calculate those changes. And it's basically like that 2-part calculation where you got your stoichiometry calculation followed by your equilibrium calculation. So the example that we went over last week was this sort of example here, where you've got a buffer solution where you have 0.5 molar weak acid and conjugate base, and you add 0.1 mole of acid to it. This would represent the stoichiometry calculation. So you set up your table like this. It sort of looks like an ice table, but it's not an ice table. It's just a table that tracks the progress of your neutralization reaction. The strong acid that you add in this case is going to get neutralized by the weak base that's already in that buffer. So in this example, we're adding 0.1 mole of the acid, right? And of course, that's going to consume 0.1 mole of your base. So your base's concentration is going to go down by 0.1 moles, and your the amount of acid is going to go up by 0.1 moles. And so that gives you a new concentration of acid and base that you can then carry over to perform the equilibrium component of the calculation. And there's one of 2 approaches that you can take. Remember, you can do the traditional equilibrium approach where you have the ice table and your quadratic equation and this and that. Or you can use the Henderson-Hasselbalch equation, which I don't have written on the screen here, but remember that's pH is equal to pKa plus the log of the ratio of the concentration of base to your concentration of acid. Obviously, I prefer using the Henderson-Hasselbalch equation, which we introduced back in Volume 1 of this aqueous ionic equilibrium series. It's a very, very convenient way to calculate the pH of a buffer solution. So that was Volume 2 in a nutshell. So what are we going to talk about tonight? Well, tonight we're going to talk about the effectiveness of a buffer solution. We're going to talk about the effectiveness of a buffer solution. So of course, the function of a buffer is to resist changes in pH. And the truth is, not all buffer solutions are created equally. Some buffers are better at resisting changes in pH than other buffer solutions. And there's 2 main properties that we're going to talk about that describe the effectiveness of a buffer. And one of them is called buffer range, and the other one is called buffer capacity. And in addition to that, we're going to talk about 2 factors that influence the effectiveness of a buffer. One of them is the relative amounts of acid and base. So in other words, what your ratio of base to acid is within your buffer solution. How does that affect the effectiveness of a buffer? And we're also going to talk about absolute concentrations of acid and base. In other words, how much acid do you have? How much base do you have in your buffer solution? Let's start by talking about those 2 factors, starting with the relative amount of acid and base. So in order to sort of introduce this concept, I'm going to demonstrate how this works. So we're going to consider two buffer solutions, right? So let's imagine that we have two 1 liter buffer solutions, and let's say they both have the same weak acid and conjugate base in them. And let's say that the pKa of that weak acid is 3.00. Remember, pKa, that's just the negative log of Ka, Ka, of course, being the acid dissociation constant, the equilibrium constant associated with that acid reacting with water, right? Let's say that pKa is 3.00, and let's say that we add 0.010 moles of sodium hydroxide to each of these 1 liter buffers. Now, what's different about them? Let's say that for buffer 1, we have 0.10 molar of the acid and 0.10 molar of that acid's conjugate base. And let's say that in buffer 2, we have 0.17 molar of the weak acid and 0.030 molar of the conjugate base of that weak acid. So in both of these cases, the sum of the concentrations of weak acid and conjugate base is 0.2. But notice that the relative amounts of acid and base in each of these buffer solutions is different, right? In buffer number 1, the relative amounts are equal, right? The amount of acid is equivalent to the amount of base. And in buffer 2, there's significantly more acid than there is base. So let's calculate the percent change in pH, right? Using the methodology that we're already familiar with that we looked at back in volume 2, let's calculate the percent change in pH of both of these buffer solutions if we were to add 0.10 moles of sodium hydroxide to each of these buffers. So what I'm going to do is I'm going to sort of copy, I'm just going to copy this information down for buffer number 1. And then what I'm going to do is I'm going to paste that into the whiteboard, and we're going to calculate percent change in pH upon adding 0.01 moles of sodium hydroxide. So let's take us to the whiteboard. Okay, so there we are. I'm going to paste the information about buffer number 1. So this is buffer number 1. We have 0.1 molar of the acid, 0.1 molar of the base. The pKa of the acid is 3.00, and we want to know what happens to it when we add 0.01 moles of sodium hydroxide, right? So the first thing that we want to do is we want to calculate the pH of this buffer solution before we add any of that sodium hydroxide, right? So I'm going to say that the pH, initially, I'll just give it a subscript of I for initial, right? Well, we can use the Henderson-Hasselbalch equation here, right? pH is equal to pKa plus the log of concentration of base over the concentration of the acid, right? So pKa, what is that? Well, that was sort of given by the problem, right? That was 3.00. And then concentration of base over concentration of acid, what is that going to be? Well, that's going to be 0.1 over 0.1, right? So we have 0.1 over 0.1, right? So 0.1 over 0.1, that is, of course, 1. Anything divided by itself is 1. So what we have here is the log of 1, and the log of 1 is actually 0, right? 10 to the 0 power is 1. Remember, the logarithm is the power to which 10 must be raised to achieve the number inside that logarithm, right? So this whole thing cancels out because log of 1 is 0. So really, the initial pH of this buffer is simply the pKa of the weak acid, which in this case is 3.00, right? So we've completed that part of the problem, right? Now what we have to do is we have to do both the stoichiometry calculation and the equilibrium calculation associated with adding 0.01 moles of sodium hydroxide. And the way that we do that is first write the equation for the neutralization of the sodium hydroxide, right? So we're going to add some sodium hydroxide. That's going to be neutralized by the weak acid, and that's going to produce water, and it's also going to produce the conjugate base A minus, right? And so we can set this up as that stoichiometry table, right, where we have what happens before the addition, what the addition actually is, and then after the addition. So of course, before the addition, what do we have? Well, we have 0.10 moles of the acid, 0.10 moles of the base, right? Because we have a 1 liter solution. So if we have 0.1 molar in a 1 liter solution, and that means we have 0.1 moles of each of these, right? The addition, we said, was 0.010 moles of sodium hydroxide, and we're not adding anything else to this, right? So that's going to consume 0.010 moles of our weak acid, resulting in 0.09 moles of the acid. So the amount of the acid in moles has reduced by 0.01 moles. At the same time, the amount of our base is going to increase by 0.01 moles. So we end up with 0.11 moles of our weak base, right? So these are our new amounts of base and acid, or our new concentrations, if you will, that we can use. And we can now use the Henderson-Hasselbalch equation once again to determine what our final pH is. So I'll go ahead and do that. So I'll say that our pH, I'll just give it a subscript of F for final, is going to be equal to pKa plus the log of concentration of base over acid. So pKa, that's for 3.00, that was given by the problem, plus the log of, again, it's base over acid, right? So we're going to have 0.11 moles over 0.09 moles, right? And I'm using moles because it doesn't matter. We can either use moles or concentration because they're both in the same solution. They both have the same volume. So in this case, the ratio of the amounts in moles is the same, is equivalent to the ratio of the molar concentrations of these species, right? So we end up with this equation here. So if we plug this into our calculator, what are we going to get? If anybody would like to participate, it's your time to shine. I will shout you out and acknowledge you if you'd like to drop your answer to this in the chat. I've already calculated this ahead of time. I did my homework. I came prepared, so I don't actually have to use my calculator in the middle of the stream, which is good because I'm actually having a hard time locating my calculator right now. Oh, here it is. Hang on. All right. So if I need it, my calculator's right here. But I shouldn't because I've already done these calculations ahead of time. So, okay. So 3 plus the log of 0.11 over 0.09. I'm trying to get this little thing out of the way here. I don't know how to do that. There we go. Okay. That's going to be equal to, what was it? That's 3.09, right? So our final pH is 3.09, and I'm going to sort of erase some stuff here to sort of condense things down a little bit. I guess I can erase this whole table here too, because we have our initial pH, we have our final pH, so we're in a good position here where we can calculate the percent change in pH. So we have, take this whole thing and drag it up here, place that, drag this guy here, right? So now we have to calculate the percent change. That's pretty straightforward, right? Percent change in anything, right? I'll just call it percent C for percent change. The percent change in anything is going to be final minus initial over initial times 100%, right? So that's going to be 3.09, that's the final pH, minus 3.00, that's the initial pH, divided by the initial pH, that's 3.00. And then, of course, it's going to be times 100%. So again, it's just final minus initial over initial times 100%. That's how we get the percent change of anything, right? And that is going to be, let's see, so the percent change in this case is going to be, what did I get? By the way, again, if anybody wants to chime in with their answer to this, you are more than welcome to do that. So we have, what is it? I got 3.00%. Okay, so we have just figured out that if you have a buffer in which you have 0.10 molar of the weak acid and its conjugate base, and that weak acid has a pKa of 3, then the percent change upon adding 0.01 moles of hydroxide ion is going to be 3.00%, right? So we just figured out that buffer number 1, we just figured out the percent change in pH associated with buffer number 1, right? So now what we're going to do, looks like I'm off the page here. I just realized that. I just realized that my own camera capture is sort of in the way here, so I'll take that. There we go. Okay. So the percent change for buffer number 1 is 3.00%. So I'm going to keep that up on the whiteboard, and I'm going to sort of erase everything else. And then we're going to do that same sort of approach, that same calculation with the buffer number 2, and we're going to compare them to see how the relative amount of weak acid and weak base influences the effectiveness of our buffer. Obviously, the buffer that has the lowest percent change is going to be the more effective buffer. Why? Because again, the main function of a buffer is to resist changes in pH, right? So the whole point is to resist, to have the pH change by as little of an amount as possible. So I'm going to go ahead and go back into my PowerPoint real quick and just copy the information for that buffer number 2, and we can perform a similar calculation where we find the percent change of the pH upon adding 0.01 moles of sodium hydroxide. So here we go. So this is buffer number 2. So we have 0.17 molar of the weak acid. We have 0.030 molar of the conjugate base of that weak acid. So we're going to go ahead and calculate our initial pH. So pH sub I, that's going to be equal to the pKa, 3.00, plus the logarithm of concentration of base over concentration of acid. So concentration of base, that's 0.030, and the concentration of the acid, that's 0.17. So if you throw that into your calculator, what do you get is the question. And when I did this, what I got was 2.25. So our initial pH is 2.25. And just like we did in the previous example, we're going to calculate the final pH using that 2-part calculation where we do the stoichiometry and the equilibrium calculation, right? So we're going to go ahead and set up our little stoichiometry table here, right? So we have, we're just going to go ahead and write the neutralization reaction equation, right? So we're going to add, we're going to add some hydroxide ion, right? That's going to neutralize, or that's going to be neutralized by the weak acid to produce water and our conjugate base, right? That'll always be the case when you're adding base, right? It's going to be neutralized by your weak acid to produce water and the conjugate base of that weak acid. And then we're going to have 3 rows in this table where we have the conditions before the addition, we have what the addition is, and then we have the conditions after the addition, right? So before, what do we have? We have 0.17 moles of the acid. We have 0.030 moles of the base. The addition, which is the same as it was in the previous example, was 0.010 moles of hydroxide. That means that the amount of our weak acid is going to decrease by 0.010 moles. So that's going to result in 0.16 moles of our weak acid after the addition of sodium hydroxide. Simultaneously, the concentration, not the concentration, but the amount of our base is going to increase by 0.01 moles. So that's going to be 0.04 moles. That is the amount of our base in this new set of conditions here, right? So now what we can do is we can just use that Henderson-Hasselbalch equation once more to calculate the final pH, and then we can do that percent change calculation. Same thing as what we did previously. So let me see if I can find some room here. Not sure how I can squeeze this in. Maybe if I, let's see, I'm going to try something. I'm going to resize myself here. Here we go. I just minimized myself. Okay, so again, we're going to use the Henderson-Hasselbalch equation, right? So it's pH is equal to pKa plus log of base over acid. So pKa, that's 3.00, plus the logarithm of base over acid. So our base in this case is 0.04. moles, and our acid is 0.16 moles. So let's see what this gives us for our final pH. Again, anybody wants to chime in with their answer, I am happy to compare yours against mine, because it's entirely possible that I miscalculated. It happens all the time. So what did I get? Well, I got a final pH sub F of, I'm going to erase this to give myself more room. The value that I got was 2.40, right? 2.40. So we have our initial pH, we have our final pH. Now we can calculate the percent change associated with buffer number 2, right? The percent change is going to be 2.40 minus 2.25 divided by 2.25 times 100%. And what is that going to, let's see, 2.40 minus 2.25 over 2.25 times 100. The value that I got was 6.67%. 6.67%. So I'm going to go ahead and sort of condense everything down here. So we have that change, so we can get rid of all of that. Let's see. Grab that, just bring it over here, grab this whole thing, and bring it up there. So we have both of our percent changes in pH. So in buffer number 1, our percent change was 3, and in buffer number 2, our percent change was 6.67. And so the question then is, which of these two buffers was the most effective? Well, that would be buffer number 1, right? Because the pH changed by a lesser amount. And again, the whole point of having a buffer solution is to resist changes in pH. So it looks to me like the closer the concentrations of acid and base are to one another, right? The closer the ratio of base to acid is to 1, the more effective the buffer will be if everything else is the same, which is true. So we've just sort of discovered that relationship by comparing these two buffer solutions. And so I'm going to go back to the PowerPoint real quick and sort of continue here. Let's see, so we have, okay, there we are. So yeah, we just discovered that relationship where the closer the concentrations of the weak acid and the conjugate base are to one another, the more effective your buffer will be at resisting changes in pH, right? And as a general guideline, for a buffer to be considered effective, the concentration of base, concentration of acid ratio has to be in the range of 0.10 to 10. In other words, the acid can be no more than 10 times more concentrated and no less than 0.10 times as concentrated as the base. So it could either be 10 times larger or 10 times smaller than the concentration of base in order for it to be an effective buffer solution. So that is how the relative amounts of acids and bases in your buffer affect the effectiveness of that buffer solution. So now we're going to switch gears a little bit. So we talked about relative amounts of acid and base. Now we're going to talk about absolute concentrations of acid and base. So in other words, how much acid, how much base in total you have in your buffer solution. So just like the last example, we're going to consider two 1 liter buffer solutions with the same conjugate acid-base pair in which the pKa is 3, and we add 0.010 moles of sodium hydroxide to each. Buffer number 1, we'll just say that that's the same as buffer number 1 in the previous example, and let's say that buffer number 2 is, instead of 0.1 molar and 0.1 molar for the weak acid and conjugate base concentrations, let's say we have 1 molar of the weak acid and 1 molar of the conjugate base. So in other words, the concentrations of the acid and base in buffer number 2 are 10 times as concentrated as the concentrations of acid and base in buffer number 1, right? So the concentration in buffer number 2 are more by a factor of 10, right? So we're going to do the same thing where we're going to go to the whiteboard and we're going to figure out the percent changes in pH of these two buffers and compare them to one another to see what effect the absolute concentrations of acid and base have on the effectiveness of your buffer solution. So once again, we're going to go back to the whiteboard here. So buffer number one, right, we already calculated that one. There's a reason why I chose the same one, because I wanted to make sure that this was somewhat easy to do, right? So buffer number one, we've already calculated the percent change, that's 3.00%, but now we have a different buffer number two, right? So I'm going to delete the buffer number two from that previous example, and I'm going to paste in the information for our new buffer number two, now that we're comparing absolute concentrations, not relative amounts, right? So give me just a second. I'm going to that information real quick. So here we go. All right. So there it is. So I'll go ahead and just ask you guys right now, what do you think is going to happen here? Do you think that the percent change in pH upon adding 0.01 moles of sodium hydroxide is going to be higher, or is it going to be lower for buffer number two than it is for buffer number one? Well, let's go ahead and find out, right? So the initial pH, we'll go ahead and calculate that, right? So the pH initially, again, let's use the Henderson Hasselbalch equation, pKa 3.00 plus the log of concentration of base over acid. In this case, it's 1 over 1, right? 1 over 1 is 1, so you have the log of 1, which is 0. So just like in buffer number 1, the initial pH is the pKa, which is 3, right? So anytime the concentrations of weak acid and conjugate base in your buffer are equivalent, then the pH of your buffer solution is going to be equal to the pKa of that weak acid, right? That'll always be true. So that's our initial pH, so we can calculate final pH by doing the stoichiometry and equilibrium calculations. So we'll set up our table here. So we have our hydroxide ion, right? That's the addition. It's going to be neutralized by the weak acid to produce water and the conjugate base, right? We have our three rows where we have the conditions before the addition, we have what the addition is, and we have the conditions after the addition, right? So initially, we have 1.00 moles of our acid, 1.00 moles of our base. The addition given by the problem is 0.010 moles of that hydroxide ion. So that means the amount of our weak acid is going to decrease by this amount here, and the amount of our weak base is going to increase by this amount here. So the amount of our weak acid becomes 0.99 moles, right? 1 minus 0.01 is 0.99, and consequently, the amount of our weak base is going to increase by 0.01 moles, so that becomes 1.01 moles, right? 1.01 moles. So I'm going to grab this whole table here and just kind of move it into the corner, give myself a little bit more room, calculate the final pH, right? So if we're calculating final pH, again, we're just going to use the Henderson-Hasselbalch equation. pH is equal to pKa, 3.00 plus the log of base over acid. In this case, base is 1.01, acid is 0.99. And so if anybody wants to punch this into their calculator and compare your result to mine, I would appreciate it, because like I said, there is entirely a possibility that I am incorrect, that I miscalculated something. All right, so the value that I got for the final pH is, what did I get? I got 3.01. 3.01. So I'm going to go ahead and just erase all this calculation mumbo jumbo. Go ahead and erase this too. I won't be needing it anymore because I got what I wanted out of it. So we have our initial pH, we have our final pH. So now we can calculate the percent change in pH, right? So the percent change is going to be final, that's 3.01, minus initial, 3.00, divided by initial, that's 3.00 times 100%. So that value ends up being 0.333%. So it's a very, very small change percentage-wise in pH upon adding that sodium hydroxide. So let me just erase everything that I no longer need here. And sort of bring this all together. Now we can compare them sort of side by side here, right? So notice that the percent change in pH of the more concentrated buffer solution is significantly less than the percent change in the more dilute buffer solution. So as the absolute concentrations of acid and base increase, the buffer becomes more effective. It becomes better at resisting changes in pH when you add strong acid or strong base to that buffer solution. So we have figured that out just by demonstrating it through comparing these two buffer solutions. So I'm going to go back to the PowerPoint quick, and let's see, PowerPoint. All right, so we figured that out. So this basically is just reiterating here what we just discovered, which is that the buffers are most effective when the concentrations, the absolute concentrations of the acid and the conjugate base are at their highest, right? So now that we've understood the effect that both relative amounts of acid and base and absolute concentrations of acid and base have on the effectiveness of a buffer, we can now understand and define the terms buffer range and buffer capacity, starting with buffer range. So the buffer range is defined as the pH range over which a particular conjugate acid-base pair can be considered effective. And that turns out to be plus or minus, or excuse me, the pKa of that acid plus or minus 1. And so to demonstrate this, I'm just going to go back to the whiteboard real quick. So take you back to the whiteboard for just a moment here. I'm going to delete everything here. So a moment ago, excuse me. All right. So a moment ago, we established that the when we were talking about relative amounts of acid and base, is that the conjugate or the acid to conjugate base ratio in a so-called effective buffer has to be between 0.1 and 10, right? The acid can either be 10 times less concentrated or 10 times more concentrated between that range in values in order for it to be an effective buffer. And so if we, let's say we use the Henderson-Hasselbalch equation to describe that, right? It would be pH is equal to pKa plus concentration of base over acid, right? So at the lower end of that range, the ratio of base to acid would be 0.1, right? Now the log of 0.1 is -1, and so we end up getting pH is equal to pKa minus 1, right? And then at the upper end of that ratio, we end up getting pH is equal to pKa plus the log of 10, right? If your base to acid ratio is 10, that's the upper end of that range. What's the log of 10? Well, that's 1, right? 10 to the first power is 10, obviously. And so we have pKa plus 1. And so it kind of makes sense that the effective range of a buffer is pKa plus or minus 1, because that kind of coincides with that general guideline where the base to acid ratio can be anywhere between 0.1 and 10, right? So just wanted to sort of point that out. So let's go back to the PowerPoint real quick. We have just a couple more things to talk about before we wrap it up for the night. And one of those things is buffer capacity, right? So buffer capacity refers to the amount of base or acid that you can add to that buffer without destroying the effectiveness of the buffer. And so what does it mean to destroy the effectiveness of the buffer? That just means you have consumed all of the weak acid or all of the conjugate base that's in that buffer, and so there's no longer any base or acid available to neutralize any additional acid or base that you might add to the buffer later on, right? And this one is actually pretty intuitive. It's pretty obvious. And buffer capacity increases with increasing concentrations of acid and conjugate base. So the more concentrated your buffer solution is, the higher your buffer capacity is, which means the there's going to be a larger amount of acid or base that you're going to have to add in order to destroy the effectiveness of that buffer. And so a typical question around buffer capacity might look something like this, where this question asks us if you have a 1 liter buffer solution and it is 0.20 molar in carbonic acid and 0.04 molar in sodium carbonate, then which of the, actually should be sodium bicarbonate. I made a mistake there. Let me fix that. So instead of, where am I? Should be NaHCO3, right? Because bicarbonate ion is the conjugate base of carbonic acid. So let me put this back on the board here. Let's say we have, whoops. Okay, so let me try that again. We have a 1 liter buffer solution that has 0.20 molar carbonic acid and 0.04 molar sodium bicarbonate. And it says, which of the following will destroy the buffer? And I accidentally took you to the slide that had the answer on it. Wow, this really isn't going well. So I guess we should go through the motions anyway, just for the sake of it. So which of the following actions will destroy this buffer? A, which is to add 0.05 moles of HCl. B, which is to add 0.05 moles of sodium hydroxide. And should be C. Man, I am just making all kinds of mistakes right now. Let's see. Okay. It's okay to make mistakes, I suppose, right? And C, which is none of the above, right? So adding 0.05 moles of hydrochloric acid, adding 0.05 moles of sodium hydroxide, or neither. Neither of these will destroy the buffer. So which of these do you think is the correct answer? That's a trick question because I've already showed you the correct answer. The correct answer is A, adding 0.05 moles of hydrochloric acid. And the reason why adding 0.05 moles of hydrochloric acid will destroy this buffer is because the buffer only has 0.04 moles of the base in it, right? So if you add as much or more acid than can be neutralized by the base, then that's going to destroy the buffer. So anytime you're adding enough acid to neutralize all of the base that's in there, or anytime, conversely, you're adding enough base to neutralize all of the acid that's in there, that's going to destroy the buffer. In other words, the buffer will no longer be able to resist changes in pH upon adding an acid or a base to it. All right, everybody, so that is going to be it for tonight. Tonight's stream was somewhat short. The reason why it was short is because we have a lot of content coming up in the next stream. Next stream, we're going to talk about titrations. Really excited to talk about acid-base titrations. It's actually a very, very fun experiment. Hopefully, in your class, you'll be able, in the lab component of your class, you'll be able to actually perform an acid-base titration because it's pretty cool. It's a fun experiment to do. So we're going to talk about all the ins and outs of performing an acid-base titration: strong acid, strong base, strong acid, weak base, strong base, weak acid, all that kind of stuff, and all the calculations that are associated with titrations and pH curves and things like that. So really excited to bring that content to you. If you found this stream valuable, I would highly appreciate your leaving a thumbs up on it. It goes a long way to help with discoverability. And thank you everybody for watching. Super appreciate it. And all right, love you guys, and I hope to see you in next week's stream. Take care.